This is the third in a series of videos in which I'm attempting to repair a fault with my Rigol DP832. In the previous video it appeared that I'd got on top of the fault, but I wasn't too confident about it. I did say I didn't think we'd really found the root cause of the problem, and sure enough the fault has returned. It's now rebooting itself on a fairly regular basis. And I want to investigate this further. I will be retiring this power supply. It's been a pain since I got it, and I've lost all faith in it. So I won't be using this. I will be replacing this. I'll show you what I'll be replacing it with in the next few days. But I still want to investigate this, see if we can find a permanent fix for the fault that will at least assist anyone else that has one of these. It does seem like it's a fairly common problem, and even in later units it does seem that this fault seems to come and go and is fairly random. And looking at the information online, it looks like people have tried various things, but in response to my previous video in this series, someone left a very good remark, a very good comment. And it's something that I've always done when repairing equipment, and in essence it amounts to don't take it apart, turn it on. And what I basically mean by that, and I think what the commenter meant as well, is you can get a lot of information before you start dismantling things by seeing what they're actually doing. Now that's the opposite of what I do when I'm restoring things, of course. If I'm restoring equipment, I just take it apart first and go right through the whole thing. But for a repair on a newer piece of equipment like this, I tend to do the opposite, and I'll spend usually quite some time going through investigating what it's actually doing. Now something like a linear supply, there are two main parts to it. You've got the analog power supply part of it, and then you've got the digital control side of it. And I mentioned in the previous video that I think the problem resides somewhere in the system watchdog or supervisor, and I think it's detecting a brownout or something like that. I haven't really looked at the processor type yet. We'll do that in this video. But I just wanted to show something that I have found so far that tends to back up that assumption, and I just wanted to demonstrate this rather than just state what's going on. So I'll get this booted up. I've got the scope connected to the supply output, and I've got the Kunkin KP184 connected to the output as well. So we'll power up the supply. I'll set it to 12 volts at 2 amps. I've got the Kunkin set for constant resistance at 10 ohms, and I've got the scope set to trigger on the falling edge of the input signal at a level of about 11 volts. So in other words, I'll do a single shot and the scope will be triggered when the supply resets. So I'll get it booted up and we'll get the test underway. Okay, so we'll get the supply set up. So 12 volts at 2 amps. We'll turn on the Kunkin, so we are now drawing a load from the supply. I'll set the scope up for a single shot, and we'll now wait until the supply resets itself. It's been getting progressively worse again, so it should only take a few minutes before it resets, and then we should see what's going on the scope. But I'll fast forward up to the point where it resets, but we need to keep a careful eye on exactly what's going on when the power supply does finally reboot itself, because there is some information there that could be important in helping us to determine the actual cause of the fault. So we'll just sit around now and twiddle our thumbs until the supply decides to misbehave. Okay, well, it finally reset. As luck would have it, it took nearly 2 hours that time, but it does seem to be completely random. Sometimes it's a minute, sometimes it's an hour or longer. But the important thing to notice here was that the voltage did not drop off as soon as the unit went into reset, it didn't drop off until the firmware started back up, and then it initialized the analog boards and presumably set the outputs to 0. Now, I've tried this on all 3 channels, and I've tried it with multiple channels running at the same time, and it always does the same thing when it resets. That is, the analog boards all seem to carry on running fine. The voltage output stays correct, and then the output voltage drops off once the firmware has reinitialized, and that tends to indicate that the problem is definitely on the control board rather than the analog board. In other words, it doesn't seem to be a big spike in the supply or anything like that, because otherwise we would see that on the output. So the next thing I'm going to look at, I'm going to tear this apart again, and we'll look at the control board. I don't know what processor is in here yet, but we'll have a look at it, and I suspect it's a brownout or some sort of watchdog timeout, something like that, but obviously we need to have a closer look at it, and I need to get inside and see what's going on. Okay, well, as you can see, I've got the unit taken back apart, and taken the control board out of the front assembly, and unfortunately when it's in you can only see the back of it, otherwise it might have started making sense a lot sooner. And as soon as I turned this over, kind of started to realise what the problem might be. If you're not familiar with these are iMX28 series processors, and really don't like these in instruments. There's nothing inherently wrong, but unfortunately a lot of developers don't seem to be able to properly configure these, and bearing in mind what we saw on the analog board, I suspect this has not been correctly configured. To show what I mean by this, if we have a quick look at a couple of important pages from the datasheet. So firstly, this is a block diagram for the power handling part of this device, which is where I suspect the problem might lie. What we have is, unfortunately, this is one of these kind of all singing, all dancing devices, and they've crammed everything into this device. And as I say, unfortunately, if developers don't properly configure the board, then you can run into problems with these. So what you basically have is a device that's intended really for battery equipment, battery operated equipment, in particular lithium batteries. So what is inside here from the power handling perspective is you'd normally feed it with a 5-volt supply, a raw 5-volt supply, which is presumably what's coming from our 5-volt regulator on the analog board. That's the one that was overheating. This then goes to a DC to DC converter, and the way this whole thing is configured is you have an output from that converter that can be used to charge up a battery, or rather it senses this voltage on the battery, and from the 5-volt supply there's a charger for the battery, and the power going to the rest of the unit comes from a DC to DC converter, where the power can be switched from the incoming 5-volt supply to the internal battery, or to the battery, lithium battery that's attached. And the issues you get with this is each of these components, each of these blocks has got a brownout detection associated with it. So each of these rails that are generated, and these are all daisy chained as you can see, not only can you set the voltages on these in firmware, but also you can set the brownout limits. And this being a switching device, there's also a requirement for some external components to allow the switching converter to operate, and that generates the required internal voltages. But if there's noise, or if that's not done properly, then you end up running into problems where it detects brownouts. Also, these chips have known issues on the silicon where they can detect false brownouts as well. So if we have a look at another page from the spec sheet, this goes through various requirements for the various rails that are associated with the converter and give some information about the limits that you can expect. So for example, for some of the rails, then the limit is it's not an absolute voltage, it's a difference between the voltage that's set and the current voltage. But some, for example, the battery is an absolute value, and if the voltage goes too far out, then it will generate a brownout reset. Now the problem with this, and what I noticed on this board straight away, is that what we have for the DC to DC converter is there's an associated, it's a buck converter, so there's an associated inductor and a diode. So I suspect, looking at the board, and the only thing I can see on here that could really be part of the converter is this diode on the back, and I suspect that's the one that's feeding the 4.2 volt rail. So we'll get the multimeter in, it's set to impedance, so we should hear it beep if we find the conduction path, and I suspect it's going to be hard to do because these are on opposite sides of the board, but I think that one end of that diode is going to be connected to this, which it is. So this end of the diode is connected to 4.2 volt rail, and that is indeed the positive end of the diode. So it does look like this end of this diode is the 4.2 volt out that you would normally connect to a battery. So that is, looking at the spec sheet, that is this output here. And one thing that's not really made clear on here, although it does state it in the text, is you need to make sure these are very well filtered. If they're not, then you'll get all sorts of problems, because the noise that the converter generates will just come straight out and it'll be passed straight through into the regulator chain, and that of course will upset any of the brownout detection that's on there. Now I had a quick look around the board, and the only capacitor I can find associated with a 4.2 volt rail is this one, this 402 capacitor here, and I've searched the rest of the board. So basically I've gone from this end of this diode to every other capacitor on the board, and there are no other capacitors on this rail apart from this one. Don't know what the value is, but there should be a whole string of capacitors on that rail, because that rail is really the stabilizing rail for the entire chain, and without stabilization on this rail you'll get noise going all the way through the chain, even if there's no battery connected. Now if there was a battery connected, it kind of does most of that work for you. It acts as a very large smoothing capacitor, but even so you should still have a good range of smoothing or decoupling capacitors. So it's not just the size of the capacitor that's important, it's you need an entire spectrum of values to give you proper frequency absorption of all the noise. So what I'm going to do, just to try and see if this is possibly the main cause, I don't want to just cover it up, I want to see if this is the real cause, is I'm going to reconnect this to the 5 volt supply. I'm not going to bother reconnecting the display, so this connector normally goes to the display, and this one goes through to the analog board, and sorry, this one goes through to the keyboard, and this one goes to the analog board. For now I'm just going to connect 5 volts and see what voltages we're getting, and then we'll put a scope on here as well and see what these look like. We'll then try connecting up the display. The display of course will draw quite a lot of power, and then we'll start connecting the other parts and see what happens. And then if we are seeing a lot of noise on these rails, then we'll try and figure out what we can do about it. But also I will try inducing noise onto those rails and see if it forces a reset. Okay, something else I thought I'd show before I plug the control board back in. As I said, I'm not really impressed with the quality of this machine. Incidentally, I've got the main switch taken out of the front panel, just temporarily hooked up here so I can power it up without having the front panel in the way. If we look at this connector now, I haven't swapped this around. This is exactly how it came. But if we look at the power coming from this, so we've got the black lead is, as you can see, at the top, red's at the bottom as you're looking at it. If I connect the ground lead to black and the red lead to positive, if you look on the meter, you can see it's connected backwards. So they've actually got the black and the red wires swapped over. Now, it doesn't matter because they swapped it at both ends. It's just that the red wire is ground. So if we look on the board itself, it does actually say on here plus 5 volts is this terminal, and as you can see, it is the wrong way around. It's correct as far as the actual voltage coming down the cable is concerned, but the red and the black are reversed. Now, I haven't swapped this. You can see there's an inspection mark on here, which makes it even worse. You've got a red mark here and one on the board, and you can see they do tie up. So this is how it was manufactured, and somebody's put an inspection mark on here to say that they're happy with that. Seems a bit strange to me, but I suppose this is one of the issues we're looking at with this particular supply. So okay, what I'm going to do now is connect up the supply to this board, and then I'm going to start looking at the various voltages on here. The main one I'm interested in really is the 4.2 volts. All the rest are internal or generated internally on the main device. So what I'm going to do is get this connected up. And so ground is the outer wire, and I want to measure the voltage between ground and this point here, which is the plus 4.2 volt rail. So we'll get this powered up. You can see the LED on the board is on, so it is connected the right way around. And what I want to do now is check the voltage here. We should have about 4.2 volts, and you can see that is very high. It should not be as high as that. It's also very unstable as well. You can see it fluctuating quite wildly there. So what we'll do now is we'll get a scope on here, have a look at that rail, and see how well it is behaving. I've got a feeling it's going to be all over the place. Okay, I've got the board hooked up to the 5 volt rail as we saw, and I've got the scope connected. Ground on the scope is on 0 volts. It is floating, so it is safe to do it in this instance, but be careful if you start hooking your scope ground to any power rails. Make sure they are floating before you do that. If you're not sure, use an isolation transformer, but even so, be careful. If you're really unsure, use an isolated probe. Okay, so we'll get this powered up, and now we'll connect the scope to the 4.2 volt rail that we just looked at. It did seem very noisy using the multimeter. The scope is on a DC coupling, 1 volt per division, so let's see. It should be quite a nice steady voltage, which it obviously is not. Okay, so we're getting around 2 volts of noise on that line, and to give you some perspective on this, the brownout detection is in the order of tens of millivolts, so it's not at all surprising that this could be causing a problem. We'll look at some of the other rails and see if they're looking any better. That one's not too bad. It's not too bad. Okay, so they're noisy, but nowhere near as bad as this particular rail. We'll look at the incoming 5 volts, and again, that's not too bad. That's what's coming from the regulator that was overheating, and as you can see, that looks fine. If you recall, there wasn't any dropout on that, and so it does look like the issue is with the decoupling of the DC to DC converter. We'll look at the switching regulator. This is the inductor that's part of the converter, and what we can see is that the frequency of the noise is directly related to the switching of that converter. go back to the 4.2 volt rail. Okay, so we need to do something about this. I'm surprised it runs at all with this amount of noise on here, and that'll get worse as we put more load on it. At the moment it's not really driving anything other than the processor itself. I'm not going to bother connecting up the display in the keyboard and the analog with it like this. It's clear it's just not going to work as it should do in this manner. So I'm going to try putting a range of capacitors. I think the spec sheet recommends from something like 1N up to 100N C1 to about 4 or 5 capacitors, each with an order of magnitude increase in value, and it should go up to about 30 microfarads or so, something like that. And at the moment I don't know what that small capacitor is that's on there, but it's probably just a few nanofarads. So this is, again, it's poor design, and we'll see if we can get this working any better. If we can get that rail smoothed out, I'll try reassembling it, at least as far as connecting the other leads is concerned, and then we'll run it back up and see if it's any more stable than it was. Okay, so what I've done is fit some capacitors. I fitted 4 in total. I've got them ranging from 33 microfarads down to 10 nanofarads, and I've just put those along the border between the ground plane and the 4.2 volt rail. And what we'll do now is get this connected back up and see if we've improved matters at all. If you recall, we were getting a ripple of about 2 volts, which is kind of ridiculous. We need it to be much less than that. Okay, and so where we're going to be reading between is ground and the 4.2 volt rail again, as we were before. So we'll get the supply switched on. Well, the LED's still on, so that's a good start. And we'll have a look at the 4.2 volt rail, and that's looking much better. We're getting about a quarter of the amplitude signal that we were. Still a bit excessive, but we'll get a better idea if we look at the voltage that's being generated on that rail to see if it's now stable. If you recall, it was about 4.6 volts. In other words, the regulator couldn't regulate. It was just essentially random noise, and the regulator wasn't doing what it was supposed to. So we'll measure between ground and the 4.2 volt rail, and as you can see, we're now getting almost exactly 4.2 volts, and it's very stable. There's no fluctuation in there at all, so that's looking much better, and is far more likely to give us much more predictable and correct values. The 1.5 volts is also correct, as is the 1.8, which were out a bit before as well, but it's not surprising with the amount of noise we were getting. The regulator just wasn't doing its job. So what I'll do now is get this put back into the machine. I'm going to flux wash it first. You can actually see there's a lot of flux that was left from the original manufacturing. When I clean off that flux, as well as what I've added when I've added these caps, get it put back into the power supply, power it up, and see if the supply still works. Okay, I've got it more or less reconnected. I've left the main switch out in case I need to take the board back out. We'll try and power it up and see if the supply comes back to life. Okay, so it's actually running, and what I'll do now is I'm going to leave this like this now for probably at least 12 hours, see if it resets. It did survive overnight before without resetting, so it could be quite a while before I'm absolutely certain if this is a fix. I will of course be posting a follow-up video to let you know the outcome, but certainly as the board was, it definitely would have caused problems. It's the sort of thing you see a lot with this type of processor, which is why I don't really like them in instruments like this. But we'll see if this has resolved the problem. It certainly looks a lot better than it was. The pre-regulator is now at the right voltage and it's stable. but we'll see what happens, and I'll get back to you in a few days with a follow-up. Okay, just before I finish this video, it's been going now for about 2 hours and so far looks quite stable. One other thing I've noticed is this supply, it's got the millivolt option, so it's showing 3 decimal places for volts and current, and it's always had an offset, especially on channel 1. It's always shown a few millivolts error, whereas now it's showing exactly the right value, so it could well be that noise was also upsetting the measurement as well, so could well be that it may also have made the supply a lot more stable as well. If it proves to be reliable, we'll have a more of an in-depth look and see what the performance is now. I did do a performance check when I first got it, so I've got a few figures as to what it was reading, but either way it's something you'll be able to compare with your own if you have one of these.